So, hello everyone, good afternoon, and welcome to the opening session of our IVS Spring Summer webinar series. It is my great pleasure to host our first speaker, Professor Antoine Kahn from Princeton University. Professor Kahn is a world-renowned leader in the field of surface and interfaces of organic and inorganic semiconductors. Beyond his scientific achievements, Antoine is a long-standing and true friend of the Israeli material science community. As we can see here, it seems like we're all friends here. Over the years, he has maintained close collaborations, many of our researchers, and has been a frequent and very welcome guest at our local conferences. We are honored to have you here with us, Antoine. Thank you for joining us. The stage is yours.
Thank you very much. Thank you. Shalom lekulam. Good afternoon. I'm very happy to talk to you today for many reasons, but in particular because I was supposed to spend the whole month of April in Israel at the Weizmann, but the circumstances of a month ago or so decided otherwise. But I'm very glad that things have calmed down for most of you. I think probably in the north it's still hot. But at least this talk gives me a little bit the impression of being there a little bit. I want to thank Noah for organizing this webinar series and for inviting me. It's very nice and highly appreciated. So let me turn to the topic of the day. As Noah said, I've worked a lot on organic materials, organic electronics interfaces, and so on, and more recently on perovskite and 2D materials. And the talk today is a little bit different. We've been working on over the past couple of years or so on singlet fission and triplet transfer to both silicon and perovskites. But the message that I think will pass through the talk is that interfaces, the role of interface electronic structure in these systems is really essential, and that's clearly something very important. So before I talk, I start. Let me thank the people I've been working with on these topics. First, the silicon work was done mostly with the group of Mark Baldo at MIT, and the work on perovskite is done in collaboration with Dan Aron, David Kahn at the Weizmann, and Igal Levin at Hebrew U. Under a new BSF grant that we got last year. And in Princeton, the people who really did most of the work, Yutan Ren, a postdoc in my group, working on perovskites, and Shinjue and Sujin Lee, also two postdocs, worked on the silicon. And then I always have great collaboration with the group of Barry Rand and Lin Lu. So these are the people who have helped quite a bit in this work. So you all know the solar spectrum, and here I look at the solar spectrum with this vertical line here, which represents the energy gap of a semiconductor. Here in particular, it's silicon. It's right above 1.1 electron volt or so, and of course, the full spectrum has photons with lower energy here, which are not absorbed by the semiconductor. I'll come back to that. And above band gap, higher energy photons, which are in principle absorbed, but of course lead to a loss of energy through thermalization. And there are other losses, which I won't go through right now, but there is at about twice the energy gap, as I will detail a little further, above twice the energy gap, there are photons that in some materials can be utilized for singlet fission and produce um, double excitation. Let me go through that. So this is, the simple energy diagram of a simple PN junction, just to to take it as an example, with the conduction band, valence band, and PN structure. So if we look at photons which have about the right energy of the gap, they produce electron-hole pairs, and these electrons are collected on one side and the holes on the other side, and these, of course, participate in the current that you send to the load. A photon with energy smaller than the band gap will not be absorbed by the semiconductor, so it's a total loss. And a photon with energy higher than the band gap will, in principle, be absorbed. And then the carriers will rapidly thermalize down to the band edges and be collected. But this energy, this extra energy here, is really lost to heat to the material. And that is the topic of the day. So remediation to these two types of losses, for the low energy photon, eventually you can do upconversion, excited state absorption, or triplet annihilation. And for the thermalization, one process is quantum cutting, which I will not talk about today. This is another topic we're working on right now, and singlet fission. Of course, this is for a single solar cell. Everybody, of course, is familiar with the other method to treat multi-gap or multi-photon absorption with tandem cell, but this is not what I want to talk about today. So, as I said, in the solar spectrum, if you have photon with energy, twice the energy gap, there are opportunities to improve the performance of the cell through the process of singlet fission. And singlet fission, in particular in a molecule or in a system like tetrazine, which is represented here, is particularly interesting, because in tetrazine, a high energy photon, with energy at least equal to the optical gap of the material, create a singlet exciton, spin zero singlet exciton. And this exciton can decay into two spin one triplet exciton with energy about half of them. The process is slightly exothermic, endothermic, I'm sorry, but it is very efficient in tetrazine. And therefore, tetrazine is a material that has been really focused on for the application of singlet fission. So here is a simple cartoon of two tetrazine molecules. So if you imagine here these two molecules in the ground state, you absorb a high energy photon, you create a singlet, with a transition from S0 to S1, and then you have a decay of this singlet exciton through a transfer of an electron into two triplets of energy 1.25 eV, as I said. Well, what's interesting in this material is that the difference between the energy of the singlet and the energy of the triplet is large, and that happens in molecules where you have a large overlap between the HOMO and the LUMO wave functions of the molecule, such as represented here for tetrazine. And it's true in anthracene, it's true also in pantacene, but tetrazene is probably the most efficient singlet fission material of the three. Okay. So just going back to the silicon solar cell efficiency these days, the current record, I think, for a single cell is 27.8% or so. In a module, it's about 25.4%. Just for the record, the best single cell halide perovskite is at about 27.98 or so, so it just passed silicon. Very competitive. The Shockley-Queisser limit for silicon is 33.7%, and the theoretical limit with a really efficient singlet fission process for silicon would bring it to an efficiency over 35%. So this is very significant, and therefore very much interest in the process. However, transferring the exciton energy, these triplets, to the absorber, so to silicon with a gap of even 1.1 electron volt, has proven very challenging. And so research is kind of picking up a little bit following the work that I'm going to describe right now. So the talk will have three parts, a very short part on the work that we did with Baldo in 2019 on a tetrazene hafnium oxide nitride on silicon, and then the evolution of this work toward a double organic interface, tetrazene zinc PC silicon, which we published again with Baldo with the MIT group last year, and then finally the singlet fission and triplet transfer to a metal halide perovskite, and that is the structure here, which we just submitted a month or two ago. So let me start with the first one. So the first one, again, I'll go quite fast here because the study is complicated and it's not really the topic. The full topic of the talk today. Again, this was initiated by Mark Baldo at MIT, where they built a solar cell. And you have the structure right here. It's a silicon solar cell with a tetrazene, with a passivated. The surface is passivated with a very thin layer of hafnium oxynitride, and then the tetrazene layer on top, and that is then protected, encapsulated, and then contact at the back here for p-type for hole collection and electron collection. And the electronic structure of the tetrazene oxide silicon is represented here with the HOMO and LUMO levels of the tetrazene, the conduction and valence band of the oxide right there, and the silicon. So I'll come back to that in a second. So they did quite a bit of electrical measurements on it, and in particular external quantum efficiency. And I just want to show this one here. This is external quantum efficiency for this device with in blue an 8 angstrom thick oxide, in red a 16 angstrom oxide, and note that the red curve is multiplied by 6.6 or so. So everywhere in the larger wavelength part of the excitation, the ratio between the two is about 6 or 6.6 or so. But in the region of absorption in the tetrazene, this is the spectrum of absorption of tetrazene. The EQE for 8 angstrom is significantly larger, going up to about 15 times that. So why is that? There are two specific reasons. Oh, the other thing, of course, is that uh, uh, the solar cell uh, uh, efficiency uh, is significantly larger, again, for a 8 angstrom oxide than for the 16 angstrom oxide. So why all this? There are two possible causes for the enhancement of the solar cell EQE and efficiency. First, the exciton dissociation in at the tetrazine oxide interface leads to what is called electric passivation of the silicon, and therefore you have much less recombination in the silicon, or the singlet fission and subsequent triplet transfer into the silicon. It turns out to be a combination of both, and this is demonstrated through various experiments of photoluminescence versus the oxide thickness, and that demonstrates the occurrence of carrier tunneling, and photoluminescence versus magnetic field. And as you know, the magnetic field, applying a magnetic field can affect the fission process and diminish the formation or the fission and the formation of triplets. So out of these experiments, it is also quite clear that both singlet fission and transfer of the triplet to the silicon, as well as interface passivation, is important in the process. So out of all this, and again, to summarize this early study, the suggested mechanism for the charge transfer from the triplet exciton to silicon is represented here. In tetrazine, absorption of a high energy photon, formation of triplets, and these triplets dissociate at the interface between hafnium oxide and silicon, and in particular, the defect state in hafnium oxide mediates this triplet exciton dissociation. The electron is transferred directly to the conduction band of the silicon. The hole stays behind on the defect and forms, as you can see right here, a kind of a charge transfer state or charge separated state between the electron on the conduction band of silicon and the hole on the defect. And this is very important, and we'll come back again and again in the talk. And the energy of this charge transfer state, if you want, should be, if the transfer is to be successful, should be in between the triplet energy of tetrazine and the energy gap of the absorber of the silicon here. So that is very important. This charge transfer state energy should be between the tetrazine triplet energy and the silicon band gap. However, the hafnium oxide nitride also introduces other deep gap states that promote charge carrier recombination and decreases the efficiency of the process, and therefore it was necessary to move to something else. So we searched for another type of interlayer that would maintain a better integrity of the interface here. And that then we go to the second part of the talk with evolution to a double organic interface. So, looking back at tetrazine, as you know, we do a lot of electron spectroscopy and looking at ultraviolet and inverse photoemission spectroscopy. You can determine, valence state and conduction state, and therefore the the position of the HOMO-LUMO with respect to vacuum level, and that means the ionization energy and electron affinity of the material. So here, as you can see, the tetrazine has an ionization energy of about 5.5 electron volt. And if you put tetrazine straight on silicon, so here in particular N plus silicon, you see that the HOMO level is 1.5, 1.53 eV below the conduction band of the silicon. And if you remember what I just said in the previous slide, this would, if in the process of the triplet transfer with the electron in the conduction band and the hole in the HOMO level, that would create a charge separated state with an energy of 1.5 electron volt, which exceeds the triplet, the tetrazine triplet energy. So that is not going to work on a system like this. So then we introduced a second extremely thin intermediate molecule, zinc PC. And zinc PC, again, through electron spectroscopy, you can determine its ionization energy, which is 5.28 electron volts. So, 300 millivolts smaller than tetrazine. And it was then expected that the zinc PC would create some kind of a ladder structure in between the tetrazine and the silicon. And that was the idea behind this double interface. Okay, the other thing, of course, is that the zinc PC triplet energy is predicted to be slightly below that of tetrazine, and therefore the zinc PC could accept the triplet coming from tetrazine and help with the dissociation of the triplet at the interface between zinc PC and the silicon. So that was done. We looked at very carefully at the electronic structure of this double interface, tetrazine, zinc PC, silicon. Now, the silicon, of course, is always passivated with an extremely thin layer, 1 nanometer or even a little less than 1 nanometer of aluminum oxide on the surface. And here I'm going to show you two cases. The first case is for N plus silicon. Everything is deposited in ultra-high vacuum, and then using photoemission and inverse photoemission spectroscopy, we get this very alignment here. And as you can see, this the energy difference between the HOMO level of zinc PC and the conduction band of silicon. That's this charge separated, charge transfer state energy is now 1.2 electron volt, and which is in between the triplet energy and the silicon band gap. So maybe that works, and it does. It does. What you have here is the external quantum efficiency measurement for the silicon solar cell. First, the silicon solar cell without tetrazine and zinc PC, and you have it right here. But as you add tetrazine and zinc PC, you have this extra positive contribution in a region of the spectrum that corresponds exactly to the absorption spectrum of tetrazine, as I will show you again and again a little later. So clearly, the tetrazine here, tetrazine zinc PC, has a very positive impact on the external quantum efficiency with this increase at 520 nanometer or so. Okay, so again, electronic structure of this interface, very important. Let's look now at the p-type case. So p-type case, of course, the Fermi level in the silicon is at a very different position. And when you put zinc PC and tetrazine on top, then you get a very different electronic structure. And in particular, the energy difference between the HOMO level and the conduction band of silicon is now much larger. And there would be a significant electron transfer barrier from the zinc PC to the silicon. So this is not expected to work, and it does not. Again, this is the EQE for the solar cell without tetrazine and zinc PC. And as soon as you put tetrazine and zinc PC on, instead of having a positive contribution, you have clearly the shadowing of the EQE by the absorption of tetrazine. So tetrazine absorbs some photons, but the triplets or the product of that absorption is not at all transferred to the silicon. So again, great importance of the electronic structure of the interface for this process. And then you can do other measurements where you show that if you build the device with tetrazine but without zinc PC, again, not only you don't have the enhancement of the EQE, but you have, again, the shadowing, because the zinc PC is essential in the process. And also with a much thicker aluminum oxide, again, you're disrupting the tunneling of the carriers through the oxide, and the EQE decreases. So building on this, we decided to look at metal halide perovskite. This singlet fission on perovskite had not been attempted before, at least as far as I know. And we wanted to test a similar structure on a halide perovskite and see whether we were getting the same response to the interface electronic structure. So for this, of course, we needed, given that our triplet fission, our singlet fission material is still tetrazine and produces the same triplets with energy of 1.25 electron volt or so, we needed a perovskite with a band gap slightly lower than the triplet energy if we had any chance to move the triplet excitation in the perovskite. So we looked at methylammonium lead tin iodide and varying the tin content. So these are the optical absorption and with the various tin content from 0.25 all the way to 0.95. And this is the optical gap of the material, again measured from optical absorption. And the minimum is extremely soft. So, anywhere with tin content of 0.55 to 0.65 to 0.7 or so gives you an energy gap which is very close to 1.2 electron volt. And here we focused in particular on methylammonium lead tin 0.55, lead 0.45, which gives you luminescence at PL at 1028 nanometers. Some people do find the gap slightly lower than that. There are some reports of lead tin gap of 1.7, 1.8 electron volt or so, but we never measured that. We bottomed at about 1.2. So So we have, very good control on the composition of the mixed compound, and these are XPS data for the lead core level and the tin core level, going up and down depending on the concentration. And here you have the calibration for both material as a function of nominal tin or lead content. So this is very well controlled. So the next thing, of course, was to go and really carefully measure the interface electronic structure of this both of the perovskite itself and then of the two organics deposited on top. So again, here I remind you of the data that we found that I showed you for the silicon case for tetrazine and zinc PC. These are the ionization energies and electron affinity of the material, as well as for the perovskite here. So these are the photoemission and inverse photoemission data for the perovskite. And then this is the valence state for the zinc PC on the perovskite. And again, we find, a very small energy difference between the HOMO level of zinc PC and the valence band maximum of the perovskite, 30, 40 millivolt or so, at least within our accuracy. And then we put the tetrazine. Again, all this is done in ultra-high vacuum, very clean, and so on. So what is very interesting, of course, is that we do find now this energy difference between the HOMO level of the zinc PC and the conduction band minimum of the perovskite at 1.23 electron volt, which is right between the triplet energy 1.25 and the band gap of the perovskite at 1.2 electron volt. So we were really hopeful that things would work. Okay, this interfacial charge transfer state has the right energy as it had on silicon. One important thing, of course, is that when you deposit material on any semiconductor and on perovskite in particular, you need to see whether the overlayer that you put on does shift the Fermi level in the energy gap of the perovskite, in which case then you need to readjust for your interface electronic structure. And here, looking at core levels as a function of core level energies as a function of the position of the zinc PC, we see absolutely no shift. So absence of core level shift indicate the Fermi level in the perovskite does not move upon overlayer deposition. So in other words, the electronic structure that I show you here seems to be really solid. So again, to come back to the presumed mechanism that we would have here is we absorb a high energy photon in the tetrazine. We get a singlet exciton, and this gives us two triplet excitons, and these triplet excitons then move to the interface between the zinc PC and the perovskite, where it is dissociated. The electron then is injected directly to the conduction band of the perovskite. The hole stays at least temporarily on the HOMO level, forms these charge transfer state with proper energy.
Halide.
Hello?
I'm sorry.
Okay. And then we pass the excitation to the perovskite. So, of course, we needed to build a device to test this concept. And that's what we did here. The device is relatively primitive for the reason that I will explain in a second, but it is, on glass, ITO, PDOT, PSS for whole collection from the perovskite. The perovskite that we focused on is methylammonium tin 0.55, lead 0.45, I3. 300 nanometer, on top of which we have the tetrazine zinc PC. Sometimes we do not have the tetrazine zinc PC. Sometimes we have just the tetrazine, as you will see. And then on top, a electron transport layer, C60 with BCP, and then a contact ITO, and then a silver grid. Now, this is, of course, not an ideal device, as you can see, because unfortunately, electrons to be collected need to go through both the tetrazine zinc PC and then the C60 up. But to do otherwise, we would need to be able to pattern the top electron transport layer, and we did not have this ability in this system here. But as you will see, it does work. The proof of concept is achieved, although the efficiency of the device, of course, can be greatly improved. Everything was done in situ, in ultra high vacuum, and so on and so on. And the excitation, the illumination is from the top silver grid. So here, again, representation of the device. Here is the EQE of the control device without any tetrazine zinc PC. Here it is with tetrazine only. And as you can see, the EQE decreases. Why? Again, because the tetrazine, presumably because the tetrazine absorbs some high energy photons, but the product of the triplet formation is not transferred to the perovskite. And then this was the big break. With zinc PC added to the tetrazine, then we have this very significant enhancement of the EQE in the spectral region corresponding to the tetrazine absorption. Here is the tetrazine absorption spectrum taken from this paper. And as you can see, when I align, of course, the energy scale, these three peaks align very nicely with these three peaks that we get. So there is no doubt that we're getting here the benefit of the triplet formation in the tetrazine through the zinc PC into the perovskite. And these also align quite well with the three peaks that you saw on the silicon. So that there is clearly the same process taking place here. We did, many other experiments to demonstrate that indeed that was the process and not something else. Here, as you can see, these are the absorbents of just the perovskite on quartz, and then the perovskite with tetrazine, and then the perovskite with tetrazine and zinc PC. And as you can see, you cannot distinguish the blue and the red. They are exactly the same, which shows you that the zinc PC really does not do anything in the absorption process, but it is essential in the process of whether these triplets are effectively converted into collected photocurrent. So that was very important. And the other thing is that if you look at the absorption, so this is relative increase, the relative change of absorption. So absorption in the material with zinc PC tetrazine versus none divided by the control, and here it is. And the same thing for EQE, the enhancement in EQE so it's EQE with zinc PC tetrazine minus EQE control over EQE control, and they really correlate quite well over the tetrazine absorption window, which I have represented here. Another experiment we did, of course, was to change now the composition of the perovskite with now only 25% of tin and 75% of lead to get a band gap of 1.35 electron volt. And this, of course, brings the gap of the absorber much higher than the triplet energy. And as you can see, now we have decreased EQE. We're not at all absorbing the triplets in the perovskite. This is the last slide, and it has to do with now defining the internal quantum efficiency of the process, and for that we needed to define and to measure the absorptance. And the absorptance is equal to, essentially 1 minus the reflectance minus the transmittance. And therefore, the IQE is equal to EQE over A. And you can see out of these different slides that both, of course, the EQE, but also the internal quantum efficiency, when we have the zinc PC tetrazine, increases significantly in the region of absorption of the tetrazine. So we are, I think I am just out of time, and I wanted to again pass the message that, and I think that is in a sense the new message that came out of the silicon and this perovskite work, that the process of triplet transfer to the absorber is really critically dependent on the interface energetics. It's not, of course, when you have triplets, it's not a radiative process that can transmit. So you have to have some dissociation of these triplets at the interface, and whether or not it goes in really depends on the interface energetics and of course the integrity of the interface. So I showed you this concept of the tetrazine zinc PC ladder structure, yeah, we are quite happy with the demonstration, EQE, IQE, and others demonstration of this first triplet transfer to a perovskite. Where it goes from here, I don't know, because clearly the field of high efficiency solar cell is moving toward the perovskite silicon tandem cells. But I think there is still nice work to do on these photon energy control, singlet fission, quantum cutting, and so on. So with that, I'll stop and thank you for listening.
Thank you for a very interesting talk. Pleasure to have you here. And I want to open the stage for questions from the audience. If there's anybody, please raise your hand.
Right now, wait a minute, because right now I don't, my screen, I don't see any.
I don't see any Q&As. Okay, don't
hold
see
Can
on.
I
it
ask a
today.
question?
Yes, please.
Hi, Antoine. Thank you for this excellent talk. I have one question. I mean, maybe it hasn't been studied yet, but if you add those extra layers, can you comment on what possible effect this could have on device stability?
Um, so no, I cannot comment directly in that we have not done any test, any measurement, and so on. Well, tetrazine is not the most stable. There are other molecules that maybe could be used for that. The device, in any case, would be completely encapsulated, as any perovskite device needs to be anyway. Sure, it adds a little bit of complexity to the process of preserving the stability and so on. I'm not sure that the tetrazine zinc PC is less stable than the perovskite itself. But that's what I can tell you at this point. I don't have any direct information on how this thing would hold. I know that some people, there's a group in Australia working on another molecule than tetrazine, which gives triplets at about the same energy. So this is something that needs to be looked at. But at this point, that's what I have.
Thank you. Of course, the point about the enhancement of efficiency is very well taken.
Yeah. Yes. One of the things we need to do, and hopefully, is to get a better design of the device itself in order to get really at how much enhancement of the efficiency we get with this system.
Thank you.
Any more questions? Well, I have one. How do you choose the perovskites you're going to use? And is there a way around using lead as part of the perovskite?
Is there the second part of your question? Is there?
Perovskites which are not lead based.
Well, again, in this particular case, we chose this perovskite because we needed a material with a gap of about 1.2 electron volt or so. So, the tin alone does not do the trick because the gap increases again. So we needed this mixture. There might be other compositions that would fit the bill. We are going to try other acations, cesium and fermamidinium and so on. But we haven't done that yet. But these are things that we are going to do.
I'm asking because there's now big hype about machine learning, which try to at least theoretically calculate the possibilities of other combinations of perovskites. And I was wondering if you're familiar with any.
Well, I'm familiar with the idea. I have not done any work along these lines, but that's a very good point. That's a very good point.
If there are no further questions, I would like us all to thank Antoine again for having us in this wonderful afternoon. And We're next gonna meet in June 24th, meeting Barbara Hayes from Beilstein Group, talking to us mostly about how open access publications. So I'll see you in 2 months, and thank you all for
Okay.
coming.
Okay, thank you all.
Bye.
Thanks,
Bye.
Antoine.
Thank you.
Thank you, Antoine.
Bye-bye.